Hello there. Come on in and make yourself comfortable. You found Science Blanket, and I'm so glad you're here to share this quiet moment with me. Have you ever looked up at the moon and wondered why it's always showing us the same side, like a silent friend who refuses to look away? Tonight, we're wrapping ourselves in that silver glow. We aren't just looking at a rock in space, we're exploring a billion-year-old mystery that literally keeps our world steady. It's a story of rhythm, gravity, and the quiet light that guides us when the sun goes down. As we begin, imagine the moonlight touching your window, soft, cool, and perfectly still. You don't need to do any work tonight. You don't need to be a scientist. You just need to be here. If this little corner of the internet feels like home to you, I'd love for you to subscribe and join our community of sleepy explorers. Now, let's take a deep breath together. Feel your body get a little heavier with every exhale. Let your jaw relax and let the space between your eyebrows soften. The world is busy, but in here, time is moving just as slowly as the moon. Let's drift into the lunar silence together. The moon hangs in our night sky as Earth's only natural satellite, a constant companion that has watched over our planet for billions of years. This celestial body that we see glowing softly above us didn't always exist in its current form. Scientists have pieced together a remarkable story of violence and creation that explains how our moon came to be. About 4.5 billion years ago, when Earth was still in its infancy, a catastrophic event changed everything. A body roughly the size of Mars, sometimes called Theia by astronomers, came hurtling through space and collided with the young Earth in an impact so tremendous it's almost beyond imagination. The collision was spectacular, sending massive amounts of debris spiraling out into orbit around our planet. This cloud of shattered rock and molten material, spinning in the darkness of space, gradually came together through gravity's patient work. Piece by piece, fragment by fragment, the debris coalesced and cooled, forming the moon we know today. When we look up at the moon tonight, we're gazing at something ancient beyond our everyday comprehension. The moon's age has been calculated at approximately 4.51 billion years, making it nearly as old as Earth itself. In fact, the moon preserves a record of the early solar system that Earth has long since erased. Our planet is geologically active, with plate tectonics constantly recycling its crust, volcanoes bringing new material to the surface, and erosion wearing away the old. But the moon is different. Its surface is a museum of cosmic history, largely unchanged for billions of years. The oldest visible rocks on the moon date back an astonishing 4.4 billion years. These ancient stones have sat undisturbed on the lunar surface, silent witnesses to almost the entire history of our solar system. They formed when the solar system was still young and chaotic, when planets were still settling into their orbits and collisions were far more common than they are today. The moon is not just ancient, it's also remarkably dense for a satellite. When scientists measure the moon's density, they find it comes in at about 3.3 grams per cubic centimeter. This makes it the second densest satellite in our entire solar system. Only Io, one of Jupiter's many moons, is denser than ours. This density tells us something important about the moon's composition and history. The moon is made primarily of rock and metal, with a small iron core, much like the terrestrial planets. Its relatively high density is part of what makes the giant impact theory so compelling, because the moon's composition closely matches that of Earth's mantle, exactly what you'd expect if it formed from material blasted off our planet during that ancient collision. Unlike the majestic ringed planets we see in photographs from space, the Moon has no rings encircling it. Saturn's rings are perhaps the most famous, but Jupiter, Uranus, and Neptune also have ring systems of their own. The Moon, however, orbits alone, without any such adornment. It also has no moons of its own. In the grand hierarchy of celestial mechanics, the Moon is a satellite, not a planet, and it doesn't have the gravitational influence necessary to capture and hold its own smaller companions. The space around the Moon is empty except for the occasional visiting spacecraft from Earth. This simplicity makes the Earth-Moon system relatively straightforward compared to the complex families of moons that orbit the giant planets of the outer solar system. Speaking of other moons, our solar system is actually crowded with them. More than 200 moons exist in total, orbiting the various planets from Mercury out to Neptune and beyond. These moons come in all sizes, from tiny irregular chunks of rock just a few kilometers across to substantial worlds larger than some planets. In this diverse family of satellites, Earth's Moon holds a respectable position. It ranks fifth by size among all the moons in the solar system. Only 4 moons are larger than ours. Jupiter claims 2 of these giants, Ganymede and Callisto, both substantially larger than our Moon. Saturn contributes Titan, a moon so large it has a thick atmosphere. And Neptune's Triton rounds out the top 4. Despite having so many siblings throughout the solar system, our Moon remains one of the most significant. The Moon's diameter measures about 3,476 kilometers. To put this in perspective, that's roughly a quarter of Earth's diameter. When you think about it, this is actually quite remarkable. Most moons in the solar system are tiny compared to their parent planets. The dozens of small moons around Jupiter and Saturn are minuscule in comparison to those giant worlds. But our Moon is different. The Earth-Moon system is sometimes described almost as a double planet because the Moon is so large relative to Earth. No other planet in the inner solar system has a moon anywhere close to this size in proportion to itself. Mars has 2 tiny moons, Phobos and Deimos, that are little more than captured asteroids. Venus and Mercury have no moons at all. This makes Earth special. The relationship between our planet and its moon is unique in the inner solar system. This substantial size has profound effects on Earth. The Moon's gravitational pull is strong enough to raise tides in Earth's oceans, pulling the water toward it as it orbits. These tides have shaped life on Earth in countless ways, creating intertidal zones that became crucial environments for evolution, providing a rhythm that countless species have adapted to over millions of years. The Moon also stabilizes Earth's axial tilt, preventing dramatic variations in our planet's orientation that would lead to extreme climate swings. Without the Moon, Earth might wobble chaotically, making the stable climate that allowed complex life to evolve far less likely. Our large Moon isn't just a beautiful object in the night sky, it's been a crucial partner in Earth's story, influencing everything from the length of our day to the stability of our seasons. As you drift off tonight, consider that the gentle light falling across your room has traveled from a world of ancient stone, a companion that has been with Earth for almost as long as our planet has existed, shaped by violence into something that now brings us peace and wonder. If you were to walk around the Moon's equator, you would travel a distance of 10,917 kilometers. It's a long journey, far longer than most of us will ever walk in our lifetimes, yet still just a fraction of Earth's equatorial circumference. The Moon is smaller than our planet, but it's not insignificant. When we measure the total surface area of the Moon, we find something surprising and easy to visualize. The Moon's surface area is approximately equal to that of the entire continent of Africa. Imagine all of Africa, from the Mediterranean shores in the north to the Cape of Good Hope in the south, from the Atlantic coast in the west to the Indian Ocean in the east, and you're picturing roughly how much territory exists on the lunar surface. All those craters, mountains, valleys, and plains, all those ancient lava flows frozen in time, all those regions with poetic names given by astronomers over the centuries, they all fit into a space about the size of Africa. It's a helpful comparison that makes the Moon feel both vast and yet somehow comprehensible. If you could stand on the Moon's surface, you would immediately notice something extraordinary about the way your body feels. The Moon's gravity is only 1/6 as strong as Earth's. This means that if you weigh 180 pounds on Earth, you would weigh just 30 pounds on the Moon. The astronauts who walked on the lunar surface during the Apollo missions experienced this reduced gravity firsthand, and it changed the way they moved. They bounded across the surface in long, graceful leaps that would be impossible on Earth. Each step carried them forward with ease, and they had to learn an entirely new way of walking. The reduced gravity affects everything. Objects fall more slowly. Dust kicked up by footsteps arcs through the vacuum in perfect parabolas before settling back down. A baseball thrown on the Moon would travel 6 times farther than it would on Earth, given the same throwing force. It's a world where the rules of motion that we've known our entire lives suddenly change, where our intuitions about weight and falling and jumping no longer apply. Earth holds many distinctions among the planets in our solar system, and one of the most fundamental is that it's the only known planet where fire can sustain itself. Fire requires 3 things: fuel, heat, and oxygen. Earth's atmosphere provides that oxygen in abundance, making fire possible. But the Moon is different. The Moon lacks an atmosphere in any meaningful sense. There's no air to breathe, no wind to feel, no weather to speak of. Without an atmosphere, fire cannot exist on the Moon. The chemical reaction of combustion simply cannot occur in the absence of oxygen. This is why the lunar landing modules used hypergolic fuels that carry their own oxidizer, allowing them to fire their engines in the vacuum of space. It's also why astronauts must carry their own oxygen supply in tanks, carefully sealed inside spacesuits that protect them from the airless environment. The Moon does have what scientists call an exosphere, but it's nothing like the atmosphere we know on Earth. An exosphere is an incredibly thin collection of particles so sparse that they rarely collide with each other. The Moon's exosphere contains atoms of helium, neon, hydrogen, and argon, along with molecules kicked up from the surface by micrometeorite impacts and the solar wind. But calling it an atmosphere would be misleading. The density is so low that for all practical purposes, the Moon exists in a vacuum. You could not breathe this exosphere. It would not slow down a falling object. It does not scatter light or create weather patterns. It's simply too thin, too insubstantial to do any of the things that Earth's thick, protective atmosphere does for us every day. Because the Moon has virtually no atmosphere and almost no axial tilt, it experiences no seasons. On Earth, our seasons exist because our planet is tilted on its axis by about 23.5 degrees. As Earth orbits the Sun, first one hemisphere and then the other receives more direct sunlight, creating summer and winter, spring and fall. But the Moon's axis is tilted only about 1.5 degrees, so minimal that it makes essentially no difference. The Sun rises and sets on the Moon with mechanical regularity, and there are no seasonal changes to mark the passage of time. A location on the moon doesn't experience the gradual warming of spring or the cooling of autumn. Instead, temperature is determined almost entirely by one simple factor: whether the sun is shining on that spot or not. The temperature variations on the moon are extreme beyond anything we experience on Earth. When sunlight strikes the lunar surface directly, temperatures can soar to about 260 degrees Fahrenheit. That's hot enough to boil water, hot enough to make steel uncomfortably warm to the touch if you could touch it through a spacesuit. But when the sun sets and darkness falls, temperatures plummet dramatically. In the lunar night, temperatures can drop to minus 280 degrees Fahrenheit or even lower. This is far colder than anywhere on Earth, colder than Antarctica at its worst, cold enough that many materials become brittle and fragile. The swing between these extremes is enormous, more than 500 degrees Fahrenheit, and it happens in the same location just depending on whether the sun is up or down. On Earth, our atmosphere acts as an insulating blanket, moderating temperatures and preventing such dramatic swings. The oceans store heat and release it slowly. Weather systems move warm air from one place to another. But the moon has none of these moderating influences. It's exposed directly to the harsh realities of space, baking in sunlight and freezing in shadow. When we look up at the moon on a clear night, it seems to shine with a soft, silvery light. But the moon doesn't generate any light of its own. What we see is reflected sunlight, and the moon is actually not a very good reflector. The moon reflects only about 12% of the sunlight that hits it. This measurement is called albedo, and the moon's albedo is quite low. For comparison, fresh snow reflects about 80 to 90% of sunlight. Earth's average albedo is about 30%. The moon's surface is covered in a layer of fine, dark dust called regolith, created by billions of years of meteorite impacts pulverizing the rock. This regolith is dark gray, similar in color to asphalt or charcoal, and it absorbs most of the sunlight that reaches it. Despite this low reflectivity, the moon still appears bright to us because the sun is so intensely luminous, and because the moon is close enough and large enough in our sky that even 12% of sunlight reflected from its surface is enough to illuminate the night. One of the most striking features of photographs taken on the moon is how dark the shadows are. When you look at images from the Apollo missions, you see bright, sunlit surfaces next to shadows that are nearly pitch black, with very little gradation between them. This happens because the moon has no atmosphere to scatter light. On Earth, our atmosphere scatters sunlight in all directions, filling in shadows with indirect light and creating the soft, diffuse illumination we're used to. Even in shadow on Earth, you can see quite well because light is bouncing around in the atmosphere, coming at you from many directions. But on the moon, light travels in straight lines from the sun, hits the surface, and that's it. There's no air to scatter it around. Shadows are cast sharply, and if you were standing in a shadow on the moon, the only light you would see would be whatever reflects off nearby sunlit surfaces. The contrast is stark and dramatic, creating a landscape of brilliant whites and deep blacks unlike anything we see on Earth. Light is fast, but it's not instantaneous. When light leaves the moon's surface, traveling at its constant speed of about 300,000 kilometers per second, it takes time to reach Earth. The distance between the moon and Earth varies slightly as the moon follows its elliptical orbit, but on average, light takes about 1.3 seconds to travel from the moon to Earth. This means that when you look up at the moon, You're not seeing it as it is right now in this exact moment. You're seeing it as it was 1.3 seconds ago. The light that's entering your eyes left the moon's surface just over a second earlier. For most practical purposes, this delay is insignificant, but it's a reminder that light has a speed, that information cannot travel faster than this cosmic speed limit, and that even when we look at our closest celestial neighbor, we're looking into the past. The moon orbits our planet at an average distance of 238,855 miles. This number is worth contemplating for a moment. It's a vast distance by human standards, far greater than any journey most of us will ever take. To drive that distance in a car at highway speeds would take months of continuous travel. Yet in cosmic terms, it's remarkably close. The moon is our nearest neighbor in space, closer to us than any other substantial celestial body. When astronauts traveled to the moon during the Apollo program, they covered this distance in about 3 days, a journey that placed them farther from home than any humans before or since, yet still within what we might call our immediate cosmic neighborhood. To help visualize this distance, imagine lining up planets side by side in the space between Earth and the Moon. You could fit approximately 30 Earth-sized planets in that gap. Picture 30 versions of our world placed edge to edge, stretching across the darkness of space from our planet to its satellite. It's a striking image that helps convey both how far away the Moon is and yet how close it remains compared to other distances in space. The planets beyond the Moon are millions or billions of miles away, distances so vast they become almost meaningless to our everyday understanding. But the Moon sits within reach, close enough that we've sent 12 humans to walk on its surface, close enough that we can see details of its terrain with a backyard telescope, close enough to feel like a familiar companion rather than an unreachable distant world. The Moon takes 27.3 days to complete one full orbit around Earth. This is called its orbital period, and it's the reason the Moon's appearance changes in our sky following a predictable cycle. As it orbits, different portions of its sunlit half become visible to us, creating the phases we know so well: new moon, crescent, first quarter, gibbous, full moon, and back again through the cycle. Ancient peoples tracked these phases carefully, using them to measure time, to plan agricultural activities, to schedule religious observances. Many of our calendars are based on the moon cycle, and the very word month derives from moon. For most of human history, the moon was our clock and calendar, its predictable motion through the sky providing structure to our understanding of time. As the moon orbits Earth, it also rotates on its own axis, spinning like a top as it travels through space. What's remarkable is that the moon rotates at exactly the same rate that it orbits. It takes the same 27.3 days for the moon to spin once on its axis as it does to complete one orbit around Earth. This perfect synchronization is not a coincidence. It's the result of what scientists call tidal locking, a phenomenon that occurs when gravitational interactions between two bodies cause one to always show the same face to the other. Over millions of years, Earth's gravitational pull on the moon created slight bulges in the moon's shape. These bulges acted like handles that Earth's gravity could grip, gradually slowing the moon's rotation until it became synchronized with its orbit. The process took a long time, but eventually the moon's rotation period matched its orbital period perfectly, and it's been locked in this configuration ever since. This tidal locking means that the near side of the moon always faces Earth. No matter where the moon is in its orbit, whether it's rising in the east or setting in the west, whether it's new or full, the same hemisphere is always turned toward us. For all of human history, people have looked up at the same face of the moon. The patterns of light and dark that we see, the features that different cultures have interpreted as faces or animals or figures, these have been constant. The ancient Romans saw the same lunar features that you see tonight. For thousands of years, no one knew what the far side of the moon looked like. It remained hidden, mysterious, impossible to observe from Earth. It wasn't until 1959, when the Soviet spacecraft Lunar 3 flew past the moon and transmitted photographs back to Earth, that humans finally saw the far side for the first time. It turned out to be quite different from the near side, heavily cratered with far fewer of the dark planes that characterize the face we know. Although the same side of the moon always faces Earth, we can actually see slightly more than just 50% of its surface over time. Through a phenomenon called libration, we can observe about 59% of the moon's total surface area from Earth. Libration occurs for several reasons. The moon's orbit is not a perfect circle but an ellipse, so sometimes it moves slightly faster and sometimes slightly slower in its orbit, while its rotation remains constant. This means we can sometimes peek around the edge, seeing a bit more of the eastern or western limb. Additionally, because the moon's axis is tilted slightly, we can sometimes see a bit more of the northern or southern polar regions. These small wobbles and tilts add up, allowing us to see nearly 60% of the moon's surface from Earth if we observe patiently over time. Still, about 41% of the moon remains permanently hidden from our view unless we send spacecraft to observe it. The moon hasn't always been at its current distance from Earth. In fact, the moon is slowly moving away from us. Each year, the moon recedes from Earth by about 1 inch, a tiny amount that seems almost insignificant. But this gradual motion accumulates over time. Millions of years ago, the moon was noticeably closer, appearing larger in the sky and exerting a stronger gravitational influence on Earth. Billions of years from now, if this process continues, the moon will be substantially farther away, appearing smaller and dimmer in the night sky. This recession happens because of the same tidal forces that locked the moon's rotation. The moon raises tides on Earth, and as Earth rotates, it carries those tidal bulges slightly ahead of the moon. These bulges pull on the moon gravitationally, transferring angular momentum from Earth's rotation to the moon's orbit. As a result, Earth's rotation gradually slows down, lengthening our days by tiny fractions of a second each year, while the moon's orbit grows larger and it moves farther away. It's a beautiful example of how gravitational interactions between celestial bodies play out over immense timescales, constantly reshaping the dynamics of the solar system. Scientists can measure the moon's recession rate with extraordinary precision using laser reflectors left on the lunar surface. During several Apollo missions, astronauts placed specialized devices called retroreflectors at various locations on the moon. These retroreflectors are arrays of corner cube prisms, designed to reflect light directly back toward its source no matter what angle it arrives from. They're remarkably simple devices with no moving parts and no power source. They just sit there on the lunar surface, waiting for light to hit them. Scientists on Earth fire powerful laser pulses at these retroreflectors, aiming at the known locations on the moon. The laser light travels across space, strikes the retroreflector, bounces back, and returns to Earth. By measuring the time it takes for the light to make this round trip with exquisite precision, scientists can calculate the exact distance to the moon down to the centimeter. By repeating these measurements over months and years, they can detect the tiny annual increase in distance as the moon slowly spirals outward. These retroreflectors placed by Apollo astronauts decades ago are still working perfectly today. They require no maintenance, no battery changes, no adjustments. They've survived the harsh environment of the lunar surface, the extreme temperature swings, the micrometeorite impacts, the unfiltered radiation from the sun, and they continue to function exactly as designed. Observatories around the world regularly bounce laser beams off these silent sentinels, gathering data that helps us understand not just the moon's orbit but also the subtle dynamics of Earth's rotation, the distribution of mass within our planet, and even tests of Einstein's theory of general relativity. These reflectors are among humanity's most enduring scientific instruments, continuing to provide valuable data more than 50 years after they were placed on the moon by human hands. The moon's gravitational pull reaches across space and affects Earth in profound ways. Most famously, the moon causes the tides in Earth's oceans. Water is fluid and responsive to gravitational forces. As the moon orbits Earth, its gravity pulls on the water in the oceans, creating a bulge on the side of Earth facing the moon. Interestingly, there's also a bulge on the opposite side of Earth, created because the moon's gravity pulls slightly less on that far side. As Earth rotates beneath these bulges, any given coastal location passes through high tide, then low tide, then high tide again, experiencing the rhythmic rise and fall of the sea that coastal peoples have observed and studied for millennia. The sun also affects tides, though less strongly than the moon because despite the sun's much greater mass, it's much farther away. When the sun and moon align during new and full moons, their gravitational pulls combine to create especially high spring tides. When they're at right angles during the quarter moons, their effects partially cancel out, creating lower neap tides. These tides have shaped coastlines, influenced marine ecosystems, and provided humans with predictable patterns that have been crucial for navigation and fishing throughout history. The changing appearance of the moon in our night sky, cycling through its phases from new to full and back again, occurs because of the changing angle at which sunlight illuminates the side of the moon facing Earth. The moon itself doesn't generate light or change in any physical way during this cycle. Instead, the sun constantly bathes half of the moon in brilliant light while the other half remains in darkness, just as half of Earth is always in daylight and half in night. What changes is our viewing angle from Earth. As the moon orbits our planet, we see different portions of its sunlit hemisphere. When the moon is between Earth and the sunlit side faces away from us and we see the shadowed side, creating what we call a new moon. As the moon continues in its orbit, we begin to see a sliver of the illuminated portion, forming a crescent. The illuminated portion grows night by night, waxing through first quarter when we see half the sunlit side, then gibbous when more than half is visible, until finally the entire near side is bathed in sunlight and we witness a full moon. A full moon happens when the near side of the moon is completely lit by the sun, which occurs when Earth is positioned roughly between the sun and the moon. From our perspective on Earth, we're looking at the moon with the sun behind us, illuminating the entire face turned toward us. The full moon rises around sunset and sets around sunrise, spending the night crossing the sky in brilliant glory. It's the brightest the moon ever appears to us, and it has held special significance in cultures around the world. Full moons have been given names reflecting the seasons and activities associated with each month. The wolf moon of January, the flower moon of May, the harvest moon of autumn. These names connect us to agricultural cycles and natural rhythms that our ancestors lived by. Even today, when most of us are insulated from direct dependence on natural cycles, the full moon captures our attention, drawing our eyes upward to marvel at its luminous beauty. Most months contain just one full moon, but occasionally a month will feature 2 full moons. When this happens, the second full moon of the month is traditionally called a blue moon. Despite the name, the moon doesn't actually appear blue during this event. The term has nothing to do with color. The exact origin of the phrase is somewhat murky, but it has become the widely accepted term for this relatively rare occurrence. Blue moons happen roughly every 2.5 years. They occur because the lunar cycle of 29.5 days doesn't align evenly with our calendar months, which vary between 28 and 31 days. This mismatch means that occasionally, a full moon will fall on the first or second day of a month, allowing enough time for the cycle to complete and another full moon to occur before the month ends. The phrase "once in a blue moon" has entered our language as an idiom meaning something rare or unusual, reflecting the infrequent nature of this astronomical event. The harvest moon holds a special place in agricultural tradition and astronomy alike. This is the full moon that occurs closest to the autumn equinox, usually falling in September or sometimes early October. The harvest moon is distinctive because of the timing of its rising. Normally, the moon rises about 50 minutes later each night as it progresses through its orbit. But around the time of the autumn equinox, the moon's orbital path makes a shallow angle with the evening horizon. This geometric arrangement means the moon rises only about 20 to 30 minutes later each night for several nights in a row. The result is that during the nights around the harvest moon, the moon rises near sunset multiple evenings in succession, providing extended twilight and bright moonlight during the early evening hours. Before the advent of electric lighting, this extra illumination was invaluable to farmers working to bring in their crops. They could continue harvesting by moonlight, working longer hours during the critical time when crops needed to be gathered before autumn weather could damage them. The harvest moon became a celebrated event, marking the transition into autumn and the culmination of the growing season. Sometimes the full moon appears noticeably larger and brighter than usual, an event that has come to be called a supermoon. This happens when the full moon coincides with the moon being at or near perigee, the closest point in its elliptical orbit around Earth. The moon's orbit isn't a perfect circle, so sometimes it's closer to Earth and sometimes farther away. At perigee, the moon can be about 30,000 miles closer to Earth than at apogee, its farthest point. This difference in distance affects how large the moon appears to us. A supermoon can appear up to 14% larger in diameter and about 30% brighter than when the moon is at its farthest point. The difference is subtle enough that you might not notice it without a direct comparison, but when the supermoon rises on the horizon, particularly when atmospheric effects make it appear even larger, it can be a spectacular sight that draws attention even from people who don't usually watch the sky. Lunar eclipses are among the most beautiful and accessible astronomical events, visible to anyone on the night side of Earth when they occur. A lunar eclipse happens when Earth passes directly between the Sun and the Moon, casting its shadow onto the lunar surface. Unlike solar eclipses, which require you to be in exactly the right location on Earth's surface to see them, lunar eclipses can be seen from anywhere on Earth where the moon is above the horizon. During a total lunar eclipse, the moon doesn't disappear completely. Instead, it typically takes on a reddish or coppery color, sometimes called a blood moon. This coloration occurs because even though the moon is in Earth's shadow, some sunlight still reaches it. This light passes through Earth's atmosphere, which acts like a lens, bending the light and filtering out the blue wavelengths while allowing the red wavelengths to pass through. This is the same effect that makes sunsets red. That red light illuminates the eclipsed moon with an eerie, beautiful glow that can last for over an hour during the total phase of the eclipse. The concept of a day is fundamentally about rotation. On Earth, a day is the time it takes for our planet to rotate once on its axis, bringing the sun back to the same position in the sky. On the moon, a day means something different because of that tidal locking we discussed earlier. A lunar day, the time from one sunrise to the next at any given location on the moon, lasts about 29.5 Earth days. This is because the moon rotates once every 27.3 days, but it's also orbiting Earth during that time. By the time it completes one rotation, it has moved partway around its orbit, so it takes a bit longer for the sun to return to the same position in the lunar sky. This means that any spot on the moon experiences about 14.75 Earth days of continuous sunlight, followed by the same length of darkness. The slow, stately progression of the sun across the lunar sky, taking 2 weeks to travel from horizon to horizon, creates the extreme temperature variations between the long lunar day and the long lunar night. As humanity begins to contemplate more sustained presence on the moon, questions of timekeeping have become practical concerns. The moon has its own proposed time zone called Lunar Standard Time. Coordinating activities on the moon with operations on Earth presents interesting challenges. Time on Earth is measured in multiple ways, but our civil time is based on Earth's rotation and is coordinated through time zones. On the moon, with its very different rotational period and its distance from Earth, using Earth time directly becomes awkward. Scientists and planners have proposed various systems for lunar timekeeping that would be more practical for people living and working on the moon. These proposals recognize that future lunar bases and settlements will need their own temporal reference frame, just as different regions of Earth use different time zones. Lunar Standard Time would help coordinate activities, schedule communications with Earth, and provide a natural framework for daily life on the moon, even though a lunar day would bear little resemblance to the 24-hour cycle we're accustomed to. The moon has played roles in human history beyond its obvious influences on tides and timekeeping. One fascinating historical footnote involves Christopher Columbus and a lunar eclipse. In 1504, Columbus and his crew were stranded in Jamaica, and relations with the indigenous people had deteriorated. The natives were refusing to provide food, and the situation was becoming desperate. Columbus, who had astronomical tables with him, knew that a lunar eclipse was going to occur. He used this knowledge to his advantage, telling the native leaders that his god was angry with them for refusing to help and would make the moon disappear as a sign of displeasure. When the eclipse occurred as he predicted, the indigenous people were reportedly frightened and agreed to resume providing supplies. It's an unsettling story of how scientific knowledge was used for manipulation, but it demonstrates that people throughout history have recognized the predictable nature of celestial events and that the moon has been studied and its motions calculated for centuries. The Apollo missions to the moon weren't just about exploration and achievement, they were also opportunities for science. During Apollo 15, astronaut David Scott performed a simple but elegant demonstration that had been theorized for centuries but never tested in the conditions necessary to prove it conclusively. On the lunar surface, in the absence of air resistance, Scott dropped a geological hammer and a feather simultaneously from the same height. On Earth, the hammer would hit the ground long before the feather, because air resistance slows the feather's fall dramatically. But in the vacuum of the lunar surface, with no air to interfere, both objects fell at exactly the same rate and struck the ground at the same instant. This demonstration confirmed what Galileo had theorized centuries earlier, that in the absence of air resistance, all objects fall at the same rate regardless of their mass. The Moon, with its lack of atmosphere, provided the perfect natural laboratory for this classic physics experiment, and the simplicity and clarity of the demonstration captured imaginations around the world. When you look at the Moon through binoculars or a telescope, or even with the naked eye on a clear night, you'll notice that its surface is far from uniform. The lunar landscape is a complex tapestry of different features, each telling part of the story of the Moon's long and violent history. The three main types of features that dominate the lunar surface are impact craters, maria, and highlands. Impact craters are circular depressions created when asteroids, comets, or meteoroids slammed into the Moon's surface at tremendous speeds. These impacts excavated enormous amounts of material, throwing it outward to form raised rims and sometimes creating rays of ejected material that extend for hundreds of miles across the surface. The maria, which is Latin for seas, are the dark patches visible to the naked eye. Ancient astronomers thought these smooth, dark areas might be bodies of water, hence the name, but we now know they're actually vast plains of solidified lava. The highlands are the bright, heavily cratered regions that cover most of the Moon's surface. These areas are lighter in color because they're composed of different rock types than the maria, and they represent some of the oldest terrain on the Moon. The dark maria that give the Moon's near side its distinctive appearance have a fascinating origin. Billions of years ago, during a period called the Late Heavy Bombardment, the inner solar system was subjected to an intense barrage of impacts. Some of these impacts were so massive that they created enormous basins, punching deep into the Moon's crust. Over time, molten rock from the Moon's interior welled up through cracks and fissures, flooding these giant impact basins with lava. The lava flows spread across the basin floors, filling them with layer upon layer of dark basaltic rock. Eventually, the lava flows ceased, and the molten rock cooled and solidified, leaving behind the smooth, dark plains we see today. These lava flows occurred mostly between 3 and 4 billion years ago, meaning the maria are ancient features, but still younger than the highlands. The maria cover about 16% of the Moon's surface, concentrated mostly on the near side. Their dark color comes from their iron-rich composition, which contrasts sharply with the lighter, aluminum-rich rocks of the highlands. One of the most intriguing mysteries about the Moon is the striking difference between its near and far sides. The far side of the Moon has far fewer maria than the near side. While the near side has those familiar dark patches that form the patterns we recognize, the far side is almost entirely highlands, heavily cratered and bright. Scientists have puzzled over this asymmetry for decades. Why would one hemisphere of the Moon be so different from the other? Several theories have been proposed. One possibility is that the Moon's crust is thicker on the far side, making it harder for lava to reach the surface and flood impact basins. Another theory suggests that the distribution of heat-producing radioactive elements might have been uneven, with more concentrated on the near side, making volcanism more likely there. The gravitational influence of Earth might also have played a role, affecting how impacts occurred and how the Moon's interior evolved. This hemispheric dichotomy remains an active area of research, reminding us that even our closest celestial neighbor still holds secrets. The South Pole Aitken Basin is one of the most impressive impact structures not just on the Moon but in the entire solar system. This enormous basin stretches across the southern far side of the Moon, measuring about 1,500 miles in diameter and reaching depths of over 5 miles below the surrounding terrain. It's one of the largest known impact craters anywhere, testament to a collision so violent it's difficult to fully comprehend. The impactor that created this basin must have been enormous, perhaps tens of miles across, traveling at cosmic velocities when it struck. The impact would have been catastrophic, excavating enormous amounts of material and possibly penetrating through the Moon's crust into the mantle. Scientists are particularly interested in this basin because studying it might provide insights into the Moon's deep interior structure. Material from deep within the Moon may have been exposed by the impact, offering a rare opportunity to study rocks that would otherwise be inaccessible. Recent missions have targeted this region for study, seeking to unlock the secrets held in this ancient scar. Among the Moon's countless craters, the largest one visible from Earth is called Bailey. This enormous crater measures 301 kilometers wide, roughly the distance from Boston to Washington, D.C. Bailey is located near the Moon's southwestern limb, in a region that's difficult to observe from Earth because it's tilted away from us and often appears heavily foreshortened. The crater is so large that it contains several smaller craters within it, accumulated over billions of years of additional impacts. Bailey is ancient, formed early in the Moon's history, and its features have been degraded and softened by countless subsequent impacts. The floor of the crater is uneven and marked by ridges and smaller craters, giving it a rugged, complex appearance. Standing on the floor of Bailey, you would be surrounded by walls so distant they would lie beyond the horizon in multiple directions, creating a vast basin that would feel more like a plain than a crater. Tycho crater is one of the Moon's most prominent and recognizable features, even though it's not among the largest. Tycho spans over 52 miles wide, making it substantial but far from the biggest crater on the Moon. What makes Tycho so distinctive is its bright ray system. Tycho is one of the youngest large craters on the Moon, formed perhaps 100 million years ago when dinosaurs still walked the Earth. The impact that created Tycho was powerful enough to throw material hundreds or even thousands of miles across the lunar surface. This ejected material formed bright rays that radiate outward from the crater in all directions, visible even to the naked eye during a full moon. The rays are bright because the impact excavated fresh material from beneath the surface, material that hasn't been darkened by billions of years of exposure to radiation and micrometeorite bombardment. Over time, these rays will darken and fade, but for now they make Tycho one of the most visually striking features on the Moon, a brilliant splash of white against the darker surrounding terrain. The Moon's surface is absolutely covered with impact craters of all sizes. Scientists have catalogued over 300,000 craters larger than 1 kilometer across, and there are countless smaller ones. Every square meter of the lunar surface has been impacted multiple times over the Moon's long history. The distribution of craters tells us about the age of different regions. Areas with many craters are old, having accumulated impacts over billions of years. Areas with fewer craters are younger, either because they were recently resurfaced by lava flows or because they're simply more recent features. By counting craters and measuring their size distribution, scientists can estimate the age of different parts of the lunar surface and reconstruct the history of impacts in the inner solar system. This technique has been used not just on the Moon but on other planets and moons as well, wherever we have high-resolution images of cratered surfaces. The Moon serves as a reference point, a cosmic laboratory where we can study impact processes and develop methods that apply throughout the solar system. The Moon is still being bombarded by space debris today. Meteor impacts occur on the lunar surface at a remarkably high rate, over 300 times per hour on average. These aren't the giant impacts that created the large craters we can see through telescopes. Most modern impacts are tiny, caused by small meteoroids no bigger than grains of sand or pebbles. But they strike the moon at tremendous velocities, often tens of thousands of miles per hour, releasing enough energy to vaporize themselves and a small amount of the lunar surface, creating tiny craters and contributing to the gradual erosion and churning of the regolith. Occasionally, larger impacts occur, bright enough to be detected by telescopes on Earth as brief flashes of light on the lunar surface. Astronomers monitor the moon specifically to observe these impact flashes, which help us understand the current population of debris in near-Earth space and the ongoing bombardment that all airless bodies in the solar system experience. Interestingly, the far side of the moon receives more meteor strikes than the near side. This might seem counterintuitive at first, but it makes sense when you consider the geometry. As the moon orbits Earth, the far side leads the way, facing into the direction of the moon's orbital motion. It's like the front of a car collecting more bugs on its windshield than the rear window. Meteoroids orbiting the sun have their own velocities, and when the far side of the moon plows into them, the collision velocities are higher, leading to more frequent and more energetic impacts. The near side, trailing behind, is somewhat shielded by the bulk of the moon itself. This difference in impact rates has contributed to the different appearance of the two hemispheres, though it's not the only factor. Over billions of years, this preferential bombardment of the far side has added up, contributing to the heavily cratered, ancient appearance of that hidden hemisphere. On Earth, when small particles from space enter our atmosphere, they burn up due to friction with air molecules, creating the streaks of light we call meteors or shooting stars. We experience meteor showers when Earth passes through debris trails left by comets, and these can be spectacular events with dozens or even hundreds of meteors per hour. But the moon has no atmosphere to protect it or to create those brilliant streaks of light. Every particle that approaches the moon, no matter how small, strikes the surface directly at full cosmic velocity. In a sense, meteor showers on the moon are constant and invisible. There's no burning, no glowing trail, just the silent impact of particle after particle, hour after hour, day after day, slowly grinding the surface rocks into finer and finer powder. This relentless bombardment has been going on for billions of years, creating the layer of regolith that covers the moon's surface, a soft blanket of pulverized rock that recorded the footprints of the Apollo astronauts and will preserve them for millions of years in the absence of wind or water to erase them. The surface of the moon is covered almost entirely by a layer of material called regolith, a fine, powdery dust mixed with small rock fragments. This isn't soil in the way we understand it on Earth, with organic matter and living organisms. Lunar regolith is purely mineral, created over billions of years by the constant bombardment of meteorites. Every impact, from the tiniest micrometeorite to larger rocks, shatters and pulverizes the surface material. The impacts also weld particles together and create glassy beads from material that melts and rapidly cools. Over time, this endless process has ground the moon's bedrock into an increasingly fine powder. The regolith layer varies in depth depending on the age of the underlying surface. In some places it might be just a few meters deep, while in ancient highland regions it can extend down 15 meters or more. This dusty blanket is what the Apollo astronauts walked on, what their boots sank into slightly with each step, creating those famous footprints that have become iconic images of human exploration. The astronauts who walked on the moon during the Apollo missions noticed something peculiar when they returned to their lunar module after each moonwalk. The moon dust that clung to their spacesuits had a distinctive smell. Once the cabin was repressurized and they removed their helmets, They could smell the dust, and they consistently described it as smelling like burned gunpowder or spent ammunition. This was surprising because moon dust and gunpowder have completely different chemical compositions. The smell likely comes from oxidation reactions. In the vacuum of space, lunar dust has been exposed to solar wind and cosmic radiation for eons, creating reactive surfaces on the particles. When brought into the oxygen-rich atmosphere of the lunar module, these reactive particles oxidized rapidly, releasing volatile compounds that produce that acrid, metallic smell. It's a reminder that the moon's environment is utterly alien, that even dust behaves differently there than anything we encounter on Earth, and that our senses can detect these differences in subtle and unexpected ways. Lunar dust turned out to be more than just an interesting curiosity for the Apollo astronauts. It proved to be a genuine hazard. The dust is toxic and abrasive in ways that caused real problems during the missions. The particles are extremely fine but also sharp and jagged, unlike Earth dust which has been worn smooth by wind and water. Under a microscope, lunar dust particles look like tiny shards of glass, with edges that can cut and tear. This dust worked its way into everything, damaging spacesuits by abrading the fabric and working into seals and joints. The dust also posed a health risk. When inhaled, even in small amounts, it irritated the astronauts' lungs, causing what they called lunar hay fever with symptoms like congestion and throat irritation. These effects were temporary, lasting only a day or two after returning to Earth, but they raised concerns about what prolonged exposure might do. For future missions that plan longer stays on the Moon, dealing with lunar dust will be one of the significant engineering and health challenges that must be addressed. Keeping it out of habitats, off of equipment, and away from astronauts' lungs will require careful planning and innovative solutions. One of the most poignant images from the Apollo missions is the photograph of an astronaut's boot print in the lunar dust, crisp and perfect, every tread pattern clearly visible. That footprint, and the thousands of others left by the 12 men who walked on the Moon, will remain virtually unchanged for millions of years. On Earth, footprints are ephemeral. Wind erases them within hours or days. Rain washes them away. Vegetation grows over them. The countless footprints of every human who has ever walked on Earth have vanished, recycled by the planet's active geology and weather. But the Moon has no wind, no rain, no vegetation, and very little geological activity. The footprints sit exactly as they were left, frozen in time. Eventually, over millions of years, the slow rain of micrometeorites will blur and erase them, grain by grain. But for now, and for eons to come, those footprints remain, silent witnesses to humanity's brief visits to another world, marks that say we were here, we walked here, we reached beyond our own planet to touch the surface of another. The Moon exists in a near vacuum, but it's not entirely empty space around it. A thin cloud of dust surrounds the Moon, so tenuous that it's barely detectable, but it's there. This dust cloud comes from multiple sources. Micrometeorites striking the surface kick up tiny particles that can escape the Moon's weak gravity if they're moving fast enough. Comet impacts, though rare, can throw enormous amounts of material into space. Charged particles from the Sun interact with dust on the surface, giving some particles enough electrostatic charge to levitate slightly above the surface before falling back down. All of these processes contribute to a sparse but persistent cloud of dust particles in the space around the Moon. This dust is important for spacecraft operations because even these tiny particles, when encountered at orbital velocities, can damage sensitive instruments and solar panels. Understanding this dust environment helps engineers design spacecraft that can survive in lunar orbit for extended periods. Perhaps even more surprisingly, the Moon has something like a tail, similar to a comet. As the Moon orbits Earth, and Earth orbits the Sun, a faint stream of sodium atoms extends behind the Moon in the direction opposite the Sun, creating a tail that can be millions of miles long. This tail forms because solar radiation strikes sodium atoms on or just above the lunar surface, giving them enough energy to escape the Moon's gravity and stream away into space. The tail is extremely faint, invisible to the naked eye, and can only be detected with specialized instruments. It was discovered relatively recently, in the 1990s, and its existence tells us about the processes happening at the boundary between the Moon and space. The sodium comes from the lunar surface itself, likely from minerals being broken down by the constant bombardment of solar radiation and micrometeorites. The tail waxes and wanes depending on the Moon's position and the intensity of solar radiation, creating a dynamic, ephemeral feature that follows the Moon through space. The solar wind, that stream of charged particles constantly flowing out from the Sun, doesn't just pass by the Moon harmlessly. Without a protective magnetic field or atmosphere, the solar wind strikes the lunar surface directly, and over time this bombardment has implanted various gases into the lunar soil. Hydrogen, helium, carbon, nitrogen, and other elements carried by the solar wind become embedded in the mineral grains of the regolith. These implanted atoms accumulate over millions of years, creating concentrations of gases that are far higher than you'd expect on an airless body. Scientists studying lunar samples have found that the regolith acts like a recording device, capturing a history of the solar wind's composition over time. By analyzing samples from different depths and different locations, researchers can reconstruct how the Sun's output has changed over millions of years, information that's valuable for understanding stellar physics and the history of our solar system. Among the gases implanted in lunar soil, helium-3 is of particular interest. Helium-3 is an isotope of helium with 2 protons and 1 neutron, making it lighter than the common helium-4 that makes up most of the helium in the universe. Helium-3 is rare on Earth because our magnetic field deflects most of the solar wind, but on the Moon it has been accumulating for billions of years. The abundance of helium-3 in lunar regolith has led to speculation about its potential use as fuel for fusion reactors. In theory, helium-3 could fuel a type of fusion reaction that produces less radioactive waste than other fusion fuels. The energy potential is enormous. A few tons of helium-3 could theoretically power a large city for a year. However, we should note that fusion power using any fuel remains an unsolved technological challenge, and helium-3 fusion is even more difficult than the deuterium-tritium fusion that researchers are currently working toward. Still, the presence of helium-3 on the Moon has captured imaginations and appears in many discussions about the potential resources the Moon might offer to future generations. The Moon's volcanic history has left behind more than just the dark Maria. During the Apollo 17 mission, astronauts discovered something unexpected: orange soil. At first, they thought it might be some kind of oxidized material, rust-colored from chemical weathering. But analysis revealed something far more interesting. The orange soil consists of tiny glass beads, created billions of years ago when volcanic fire fountains erupted from vents in the lunar surface. The eruptions shot molten rock high above the surface where it cooled rapidly in the vacuum, forming perfect spheres of glass. These glass beads, rich in iron and titanium, have an orange color that's quite striking against the gray regolith. The discovery was scientifically valuable because it provided direct evidence of explosive volcanic activity on the Moon and gave scientists samples of volcanic glass that preserve information about the composition of the lunar interior. The orange soil remains one of the most colorful and interesting discoveries from the Apollo missions, a splash of unexpected color on an otherwise monochrome world. Deep within some of the Moon's lava tubes and caves, a peculiar substance forms that has been given the evocative name moon milk, though its technical name is selenite. This material consists of needle-like crystals, delicate formations that grow in the sheltered environments of lunar caves where conditions are more stable than on the surface. The name selenite comes from Selene, the Greek goddess of the moon, and these crystals are formations of gypsum, a hydrated calcium sulfate. The presence of water molecules in gypsum is itself interesting, suggesting that even the Moon's interior isn't as completely dry as once thought. These crystals grow slowly, molecule by molecule, creating structures that are fragile and beautiful. In the low-gravity and protected environment of a lava tube, they can grow into formations that would be impossible on Earth, where gravity would cause them to break under their own weight. These caves and their unique formations represent some of the most scientifically interesting targets for future exploration, places where the Moon's geological history is preserved in delicate crystal structures waiting to be discovered. When you examine detailed photographs of the lunar surface, you'll notice long, winding channels that snake across the Maria, sometimes extending for hundreds of kilometers. These features are called rills, and they're the collapsed remnants of underground lava channels. Billions of years ago, when volcanic activity was shaping the Moon's surface, lava didn't always flow across the surface in broad sheets. Sometimes it flowed through tubes beneath a solidified crust, much like lava tubes on Earth in places like Hawaii or Iceland. These subsurface channels allowed lava to travel great distances while staying insulated from the cold of space, remaining hot and fluid. Eventually, the volcanic activity ceased and the lava drained away, leaving hollow tubes beneath the surface. Over time, the roofs of these tubes became unstable. Without support from the lava that once filled them, sections of the roof collapsed inward, creating the sinuous valleys we see today. Some rills are quite dramatic, with steep walls and flat floors, clearly showing their origin as channels that once carried rivers of molten rock across the ancient lunar landscape. Related to the rills are features called moon pits, which form when the roofs of lava caverns collapse. These pits are circular or irregular openings in the surface, windows into the underground spaces below. Some of these pits are enormous, hundreds of feet across and equally deep. Looking into one of these pits, you would see the opening descending into darkness, the floor far below, and possibly the entrance to a larger cavern system extending horizontally underground. These pits are of particular interest to scientists and mission planners because the caverns they connect to could provide natural shelter for future lunar bases. The caverns offer protection from radiation, from micrometeorite impacts, and from the extreme temperature swings of the lunar surface. Inside a lava tube, temperatures would be relatively stable, hovering around a more moderate value year-round. These natural structures could be far superior to anything humans might build on the surface, offering ready-made habitats that would just need to be sealed and pressurized. Exploring these pits and the cave systems they lead to is a priority for future missions. The volcanic features we see on the Moon, the Maria, the rills, the lava tubes, all speak of a time when the Moon was geologically active, when its interior was hot enough to produce molten rock that rose to the surface and flooded vast regions. But those days are long gone. Lunar volcanoes were active long ago but are now dormant. The last major volcanic activity on the Moon ceased roughly 1 billion years ago, though some evidence suggests that minor volcanic activity might have continued in isolated locations until as recently as 100 million years ago. Still, for the vast majority of the Moon's recent history, it has been volcanically dead. The Moon's small size meant it cooled relatively quickly after its formation. Unlike Earth, which has a large, hot interior that continues to drive plate tectonics and volcanism, the Moon's interior has largely solidified. There's no longer enough heat to generate the large volumes of magma needed for volcanic eruptions. The Moon's surface has been essentially frozen in time for billions of years, a snapshot of ancient volcanic processes that ceased when the Moon's internal heat engine ran down. Scientists can learn about the Moon's volcanic past by studying the rocks brought back by the Apollo missions and by analyzing the composition of lunar surface materials using remote sensing instruments on orbiting spacecraft. One particularly interesting discovery is the presence of olivine-rich rocks in certain locations. Olivine is a green, iron-magnesium silicate mineral that forms deep within planetary bodies under high temperature and pressure. The presence of olivine at or near the lunar surface indicates that the Moon's mantle was once molten. Olivine crystallizes from magma as it cools, and finding it on the surface suggests that either it was brought up by volcanic activity from the deep interior, or that major impacts excavated deeply enough to expose mantle material. Either way, olivine serves as a marker, a messenger from the depths telling us about conditions that existed when the Moon was young and its interior was a churning sea of molten rock. These olivine-rich regions are scientifically valuable because they offer glimpses into the Moon's deep interior, allowing scientists to understand the composition and evolution of the lunar mantle. The Moon's internal structure, like Earth's, consists of distinct layers. Beneath the surface regolith and the solid crust lies the mantle, the thick layer of rock that makes up most of the Moon's volume. The lunar mantle contains primarily olivine and pyroxene, both silicate minerals that are common in the mantles of terrestrial planets. Olivine, as we discussed, is an iron-magnesium silicate, while pyroxene is a group of silicate minerals that also contain iron, magnesium, and calcium. These minerals tell us about the chemical composition of the material that formed the Moon and about the conditions under which the Moon's interior evolved. The presence of these specific minerals helped scientists understand how the Moon differentiated, how it separated into layers early in its history with denser materials sinking toward the center and lighter materials rising to form the crust. By studying the mantle's composition through remote sensing and analysis of volcanic rocks that originated in the mantle, researchers can reconstruct the thermal and chemical history of the Moon's interior over billions of years. The Moon's crust, the outermost solid shell, varies significantly in thickness between different regions. On the near side of the Moon, the crust averages about 25 miles thick. This is relatively thin compared to some other regions of the Moon, and it helps explain why volcanic activity was more extensive on the near side. A thinner crust would have provided less resistance to rising magma, making it easier for lava to reach the surface and flood the impact basins, creating the Maria we see today. The composition of the near-side crust is also somewhat different from the far side, with variations in the abundance of different minerals and elements. These differences reflect the complex geological history of the Moon, the way its interior evolved differently in different regions, possibly influenced by the gravitational effects of nearby Earth and by the uneven distribution of heat-producing radioactive elements within the young Moon. On the far side of the Moon, the crust is significantly thicker, reaching up to 37 miles in some regions. This thicker crust is one of the key reasons why the far side has so few Maria. When large impacts created deep basins on the far side, the thicker crust acted as a barrier, preventing or limiting the amount of lava that could reach the surface. Any magma trying to rise from the mantle had to travel through many more miles of solid rock, and often it solidified before reaching the surface, or simply never had enough buoyancy to make it all the way up. The thick far side crust is one of the defining characteristics that creates the stark difference in appearance between the two hemispheres of the Moon. Scientists are still working to understand exactly why the crust is so much thicker on the far side. It might be related to the way the Moon cooled and solidified early in its history, or to the gravitational influence of Earth affecting how the Moon's crust formed and evolved. Interestingly, while the far side generally has a thicker crust, the far side highlands, those heavily cratered, ancient regions, actually have thinner crust in some areas than you might expect. This seems contradictory at first, but it reflects the complex geological history of the Moon and the effects of billions of years of large impacts. When a truly massive impact occurs, it doesn't just excavate material and create a crater. It can actually thin the crust in that region, removing miles of crustal rock and exposing deeper layers. Some of the highland regions on the far side have been so heavily bombarded that the cumulative effect of multiple large impacts has actually thinned the crust in those specific locations, creating a patchwork of varying crustal thickness. Measuring crustal thickness from orbit is challenging, but spacecraft using gravity measurements and seismic data have gradually built up a detailed picture of how the Moon's crust varies from place to place, revealing a complex three-dimensional structure shaped by billions of years of impacts and internal evolution. The Moon is not a static, unchanging body frozen perfectly in time. It's still evolving, though at an almost imperceptibly slow rate. The Moon shrinks about 50 meters every 100 million years. This might not sound like much, and indeed it's a tiny amount compared to the Moon's diameter of over 3,000 kilometers. But it's a real, measurable process. The shrinkage occurs because the Moon's interior is still very slowly cooling. As the interior cools, it contracts, and this contraction causes the surface to wrinkle and buckle, like the skin of a grape shriveling into a raisin, though on a much smaller proportional scale. This shrinkage creates features called thrust faults, places where the crust has cracked and one section has been pushed up over another. These faults can be hundreds of kilometers long and create cliffs or scarps that rise tens of meters above the surrounding terrain. Some of these faults are quite young in geological terms, perhaps only a few million years old, and they show that the Moon is still tectonically active in a limited way, still adjusting to the slow cooling and contraction of its interior. Beneath the South Pole Aitken Basin, that enormous impact structure we discussed earlier, spacecraft orbiting the Moon have detected something unusual. Gravity measurements reveal a massive concentration of dense material beneath the basin, a metal blob or anomaly that's absolutely enormous. This structure contains roughly 5 times 10 to the 18th kilograms of mass, which is more than 2 quintillion kilograms, a number almost too large to comprehend. The anomaly extends down hundreds of kilometers into the Moon's interior. Scientists aren't entirely certain what this structure is, but the leading theory is that it's the remnants of the asteroid or comet that created the South Pole Aitken Basin. When that enormous impactor struck the Moon billions of years ago, it would have been traveling at tremendous velocity, and the impact would have been catastrophic. Most of the impactor would have been vaporized or melted, but the densest core material, rich in iron and nickel, might have survived and become embedded in the Moon's mantle. Over billions of years, this material has remained there, a buried testament to one of the most violent events in the Moon's history, detectable now only through its gravitational influence on passing spacecraft, a hidden mass lurking in the depths beneath the ancient, scarred surface. The Moon today has only a very weak magnetic field, far weaker than Earth's protective magnetic envelope. Earth's magnetic field is generated by the churning of molten iron in its outer core, a dynamo effect that creates a magnetic bubble extending thousands of miles into space. This field shields us from harmful solar radiation and cosmic rays, deflecting charged particles and creating the beautiful auroras at the poles. The Moon, however, has no active dynamo. Its small iron core has cooled and largely solidified, and it no longer generates a significant global magnetic field. What remains are just faint, localized magnetic anomalies scattered across the surface, fossil remnants of an ancient magnetic field that may have existed billions of years ago when the Moon's interior was hotter and more dynamic. These weak magnetic fields are scientifically interesting because they preserve information about the Moon's early history, but they provide no practical protection from radiation. Astronauts on the Moon are exposed to the full intensity of solar and cosmic radiation, making radiation shielding one of the key challenges for long-term lunar habitation. Despite the Moon's generally weak magnetism, there are certain locations where localized magnetic fields create visible effects on the surface. These places are marked by features called lunar swirls, bright patches on the surface that twist and curve in sinuous patterns. The most famous is Rayner Gamma, a bright swirl visible through telescopes on Earth. These swirls appear brighter than their surroundings, and they don't seem to be topographic features. They're simply areas where the surface material appears fresher and less weathered. The connection to magnetic fields provides an explanation. The localized magnetic fields, though weak by terrestrial standards, are strong enough to deflect some of the solar wind particles that constantly bombard the lunar surface. This deflection protects the surface beneath from space weathering, the process by which solar wind and micrometeorite impacts gradually darken lunar soil over millions of years. The protected areas remain brighter, creating these mysterious swirling patterns. The swirls are like magnetic umbrellas, shielding small patches of the surface and creating patterns that have puzzled astronomers for decades. Understanding exactly how these magnetic fields formed and why they create such distinctive patterns remains an active area of research. When spacecraft orbit the Moon, their paths are influenced by the Moon's gravitational field. Ideally, if the Moon were a perfect sphere with uniform density, calculating orbital mechanics would be straightforward. But the Moon's gravitational field has strange fluctuations that caused unexpected problems for early lunar missions. Spacecraft would experience slight tugs and pulls that weren't predicted by simple models. Their orbits would shift and change in ways that required constant monitoring and correction. These gravitational anomalies puzzled scientists and mission controllers until their source was identified. The fluctuations come from variations in the density and thickness of the Moon's crust and the distribution of mass below the surface. Just as mountains and valleys create slight variations in Earth's gravitational field, structures within and on the Moon create similar variations. But some of the most significant anomalies couldn't be explained by surface topography alone. Something else was causing major distortions in the gravitational field. The source of the most dramatic gravitational anomalies turned out to be mass concentrations, or mascons, dense concentrations of material beneath the lunar surface. These mascons are associated with the major impact basins, particularly those that were later filled with lava to create the Maria. When a large impact occurred, it excavated enormous amounts of low-density crustal material, creating a deep basin. Later, When lava flooded these basins, it filled them with denser basaltic rock. The result is a concentration of dense material in a localized area, creating a stronger gravitational pull in that region. Spacecraft passing over a mascon experience a slightly stronger gravitational tug, which can alter their orbit. For early lunar orbiters, these mascons caused orbital decay much faster than expected, bringing some spacecraft dangerously close to the surface. Modern missions account for mascons in their orbital calculations, but they remain a challenge for spacecraft operations, particularly for missions requiring very precise orbits. The mascons are yet another reminder that the Moon's structure is complex and that its history of impacts and volcanism has created a varied internal architecture. The gravitational anomalies associated with mascons genuinely puzzled early orbiters and mission planners. The lunar and lunar orbiter missions of the 1960s experienced unexpected orbital changes that weren't initially understood. Controllers watching the spacecraft found that orbits degraded faster than calculations predicted, and the tracking data showed variations that didn't match theoretical models. It took careful analysis and the correlation of gravitational data with maps of the lunar surface features to finally understand that the Maria were gravitationally distinct from the highlands, that there were massive concentrations of dense material beneath these ancient lava plains. This discovery was scientifically valuable, revealing information about the Moon's internal structure and the processes that shaped it, but it also had practical implications. Any future spacecraft designed to orbit the Moon long-term would need to account for these gravitational variations, either by maintaining a higher altitude where the effects were weaker, or by planning for regular orbital corrections to counteract the mascon's influence. The Moon might seem geologically dead, but it's not entirely quiet. Moonquakes occur regularly, though they're quite different from earthquakes. There are several types of moonquakes, each with different causes. Some occur due to tidal stress, the gravitational pull of Earth flexing and squeezing the Moon's interior slightly as the Moon orbits. These tidal moonquakes happen with predictable regularity, tied to the Moon's position in its orbit. They are generally small but frequent. Another type of moonquake is caused by temperature changes. As the Sun rises and sets on the Moon, the extreme temperature swings cause the surface rocks to expand and contract. This thermal stress can trigger small seismic events, crackling and popping as the rocks adjust to the changing conditions. These thermal moonquakes occur most frequently during the transition between the long lunar day and night, when temperature changes are most dramatic. Deep moonquakes also occur, originating from hundreds of kilometers below the surface, possibly caused by residual tectonic activity or ongoing adjustments in the Moon's interior structure as it continues its slow cooling. Some moonquakes originate from thrust faults visible on the surface as scarps, those cliff-like features created by the Moon's gradual contraction. These faults are not just ancient, frozen features. Some of them are active today, slipping and adjusting as the Moon continues to shrink. When movement occurs along one of these faults, it generates seismic waves that travel through the Moon. Seismometers left by Apollo astronauts detected thousands of moonquakes during their years of operation, providing the first direct measurements of the Moon's internal structure and activity. Analysis of moonquake data has revealed that the Moon's interior is partially molten, with a small liquid core surrounded by a partially molten layer. The moonquakes also showed that the Moon's interior structure affects how seismic waves travel, creating patterns that help scientists understand the composition and state of material deep within the Moon. Understanding moonquakes is important for future lunar bases because strong quakes could potentially damage structures, and knowing when and where they're likely to occur helps with site selection and structural design. Scientists have identified what they call cold earthquakes happening on the Moon, seismic events triggered by deep freezing and contraction. As the lunar night progresses and temperatures plummet to hundreds of degrees below zero, the contraction isn't just a surface phenomenon. The cold penetrates into the subsurface, causing rocks to contract and sometimes crack. This creates small seismic events, miniquakes caused purely by temperature. The term cold earthquake is somewhat metaphorical, as these aren't exactly earthquakes, but they represent a type of seismic activity that's essentially unique to airless bodies with extreme temperature variations. On Earth, our atmosphere moderates temperature changes so dramatically that we never experience anything comparable. But on the Moon, the direct exposure to space and the absence of any insulating atmosphere means temperature drives geological processes in ways that simply don't happen on Earth. These cold quakes are generally small, but they contribute to the gradual breakdown and weathering of lunar rocks over geological time. Throughout history, observers have reported strange phenomena on the Moon, brief flashes of light, or temporary changes in the appearance of certain features. These reports, collectively known as transient lunar phenomena, have been documented for centuries. Some are probably observational errors or atmospheric effects on Earth distorting the view, but some appear to be real events on the Moon itself. Modern observations have confirmed that impact flashes do occur when meteoroids strike the lunar surface with enough energy to create a brief, bright flash visible from Earth. Observers with video cameras have captured dozens of these impact flashes, confirming that the Moon is still being actively bombarded. Other transient phenomena might be caused by outgassing, the release of gases trapped below the surface finding their way to the surface through cracks or fissures. In the low pressure of the lunar environment, even a small amount of gas escaping could create visible effects. These phenomena are rare and brief, but they remind us that the Moon, though ancient and largely unchanging, still experiences events and processes that make it a dynamic world worthy of continued observation and study. The Moon's surface includes dramatic topography, with mountains rising thousands of feet and valleys plunging into shadow. Among the most impressive features are the cliffs created by thrust faults. The tallest lunar cliff drops about 1,600 feet, a sheer wall of rock rising from the surrounding plain. To put this in perspective, that's taller than the Empire State Building. Standing at the base of such a cliff on the Moon, you would look up at a towering wall of rock extending high above you. In the Moon's lower gravity, climbing such a cliff would be easier than on Earth, as would falling from it, which would happen in slow motion, giving you more time to react, though the impact would still be dangerous. These cliffs, called lobate scarps in geological terminology, are the surface expressions of thrust faults where the Moon's crust has broken and one block has been pushed up and over another. They can extend for miles, creating dramatic boundaries in the landscape. Future lunar explorers will need to navigate around these features, and they might also study them up close, examining the exposed rock faces to learn about the Moon's crustal structure and the forces that created these impressive geological structures. Deep within the permanently shadowed craters near the Moon's poles, where sunlight has not fallen for billions of years, water ice exists. These craters are among the coldest places in the entire solar system, with temperatures that never rise above about -240 degrees Fahrenheit. In these frigid conditions, water that arrives on the Moon, whether delivered by comets and asteroids or created by chemical reactions on the surface, becomes trapped. Once water molecules find their way into these cold traps, they freeze and remain frozen, unable to escape. Over millions and billions of years, Ice has accumulated in these permanently shadowed regions, building up deposits that represent an invaluable resource for future exploration. The existence of this ice was theorized for decades before it was finally confirmed through multiple observations using different techniques. The discovery has fundamentally changed how we think about the Moon and what's possible for sustained human presence there. In 2020, NASA's SOFIA, the Stratospheric Observatory for Infrared Astronomy, confirmed the presence of water molecules on the sunlit surface of the Moon. SOFIA is a modified Boeing aircraft that carries a telescope to high altitudes, above most of Earth's atmosphere, allowing it to make infrared observations that would be impossible from the ground. The observations detected the characteristic signature of water molecules at several locations on the lunar surface, including areas outside the permanently shadowed regions. This was surprising because sunlight should quickly break apart water molecules on the surface, dissociating them into hydrogen and oxygen, which would then escape into space. The detection of water on sunlit surfaces suggests that water is somehow being created or replenished continuously, perhaps through chemical reactions between the solar wind and minerals in the lunar soil, or that water molecules are somehow bound to minerals in ways that protect them from immediate destruction. This discovery opened new questions about the lunar water cycle and how water moves across and interacts with the lunar surface. The first strong evidence for water on the Moon came earlier, in 2009, when India's Chandrayaan-1 spacecraft made a groundbreaking discovery. Chandrayaan-1 carried an instrument called the Moon Mineralogy Mapper, which analyzed reflected sunlight from the lunar surface in multiple infrared wavelengths. This instrument detected absorption features consistent with water and hydroxyl molecules across much of the lunar surface. The discovery was revolutionary because for decades, the Moon had been considered essentially bone dry, any water that might have existed when it formed having been lost to space long ago. The Chandrayaan-1 findings showed that water is far more common on the Moon than anyone had imagined, present not just as ice in polar cold traps but as molecules bound to minerals across the surface. This discovery earned international recognition and demonstrated the value of global cooperation in space exploration, with India's mission contributing crucial data that changed our fundamental understanding of the Moon's composition. Estimates of how much water ice exists in the Moon's polar regions vary, but some calculations suggest there may be up to 600 million tons of water trapped in permanently shadowed craters. To put this in perspective, that's enough water to fill hundreds of thousands of Olympic-sized swimming pools. For lunar exploration, this represents an extraordinary resource. Water isn't just essential for drinking. It can be split into hydrogen and oxygen through electrolysis, providing both breathable air and rocket fuel. The oxygen could support astronauts in lunar habitats, while the hydrogen and oxygen together could fuel spacecraft for missions departing from the Moon. Having access to water on the Moon could make it a refueling station for missions to Mars and beyond, dramatically reducing the cost and complexity of deep space exploration because spacecraft wouldn't need to carry all their fuel from Earth. The polar ice deposits transform the Moon from just a destination into a potential resource that could enable the next era of space exploration. Water molecules on the Moon don't just sit still once they arrive. The lunar surface is constantly being bombarded by micrometeoroids, tiny particles that strike at high velocities. When these impacts occur in areas where water molecules are present, either bound to minerals or as ice, the impacts can release water molecules into space. Some of these molecules escape the Moon entirely, lost to the vacuum of space. Others follow ballistic trajectories, arcing through the vacuum like tiny spacecraft before falling back to the surface somewhere else. If a water molecule released from an equatorial region happens to land in a permanently shadowed crater near the poles, it becomes trapped in that cold environment and joins the ice deposits there. This process has been occurring for billions of years, gradually transporting water across the moon and concentrating it in the coldest locations. Understanding this transport mechanism helps scientists predict where the richest ice deposits might be found and informs planning for future missions to access and utilize this water. Water survives in these cold traps specifically because of the extreme cold that exists in permanently shadowed regions. The temperature is so low that water molecules that land in these areas freeze instantly and lack the thermal energy to escape. Even though the moon has essentially no atmosphere and is exposed to the vacuum of space, which would normally cause ice to sublimate and disappear, the extreme cold suppresses sublimation to negligible rates. The ice can persist for billions of years, slowly accumulating as more water molecules arrive and get trapped. These cold traps act like natural freezers, preserving not just water but potentially other volatile compounds that were delivered to the moon over its history. Studying the composition of this ice could provide information about the sources of water in the inner solar system, about the composition of comets and asteroids that have struck the moon, and about chemical processes occurring on airless bodies throughout the solar system. Despite the presence of water ice in polar craters and water molecules bound to surface minerals, the moon has no liquid surface water. The conditions necessary for liquid water to exist, a certain range of temperature and pressure, simply don't occur on the lunar surface. The pressure is far too low, essentially zero, so any ice that's heated will sublimate directly into water vapor without passing through a liquid phase. This is fundamentally different from Earth, where liquid water covers most of the surface and cycles through the atmosphere as vapor, falls as rain, flows in rivers, and fills the oceans. On the moon, water exists either as ice in the coldest locations or as individual molecules or small clusters bound to minerals. There are no lakes, no streams, no ponds. The hydrological cycle that's so fundamental to Earth's environment and to life as we know it simply doesn't exist on the moon. This absence of liquid water creates a completely alien environment and presents challenges for any future settlers who will need to extract ice and process it to obtain usable water. An intriguing and somewhat speculative idea that occasionally surfaces in discussions of lunar science is the concept of moon bugs, theorized microbes that might exist in ancient ice pockets. The idea is that if comets or asteroids containing microbial life struck the moon and deposited water that became trapped in permanently shadowed craters, those microbes might still exist, frozen in the ice, in a state of suspended animation. This is highly speculative and most scientists consider it unlikely, but it's not entirely impossible. We know that some Earth microbes can survive in extreme cold for very long periods. Bacteria have been revived from ice that's hundreds of thousands of years old. If hardy microbes from elsewhere in the solar system were delivered to the moon and quickly frozen, they might theoretically survive in the ice for millions or even billions of years. Before we begin extracting and using lunar ice, some scientists argue we should study it carefully to determine whether any such organisms exist, both for scientific reasons and to avoid potentially contaminating our activities with alien microbes, however unlikely their existence might be. The Moon's polar regions have become key exploration targets for future missions precisely because of the presence of water ice and because of their unique lighting conditions. Some locations near the poles experience near-constant sunlight for much of the year, high points on crater rims that are almost always illuminated while the crater floors remain in perpetual shadow. These locations offer the best of both worlds, access to solar power for habitats and equipment, and proximity to water ice deposits. Multiple space agencies are planning missions to the lunar poles, including NASA's Artemis program, which aims to land astronauts in the South Polar region. Robotic missions are being designed to explore permanently shadowed craters, to map ice deposits in detail, and to demonstrate technologies for extracting and processing the ice. The poles represent the most promising locations for establishing a sustained human presence on the Moon, and they offer scientific opportunities to study ancient ice that might preserve information about the early solar system. Future missions to the Moon are increasingly focused on sustainable water use, developing technologies and techniques that will allow explorers to live off the land rather than bringing everything from Earth. In situ resource utilization, using materials found on the Moon, is a key principle for making lunar exploration economically viable. Demonstrations are planned for extracting ice from regolith, melting it, purifying it, and then using it for life support and fuel production. These capabilities would transform lunar exploration from expensive, short-term visits into sustainable, long-term occupation. Imagine a lunar base where crews can produce their own water, oxygen, and rocket fuel, where spacecraft can refuel for the journey to Mars or to asteroids, where the Moon becomes not an endpoint but a way station, a stepping stone for humanity's expansion into the solar system. The water frozen in those dark, cold craters near the poles could be the key that unlocks this future, turning dreams of space settlement into practical, achievable goals, and ensuring that our return to the Moon this time is permanent. The Moon has been the target of intense robotic exploration since the beginning of the space age. Over 105 robotic spacecraft have been sent to explore the Moon, a remarkable number that reflects humanity's enduring fascination with our nearest neighbor. These missions have taken many forms. Some have flown past the Moon, capturing images as they sped by. Others have entered orbit, spending months or years studying the surface from above, mapping its topography, analyzing its composition, and measuring its gravitational and magnetic fields. Still others have landed on the surface, touching down to study the regolith up close, deploy instruments, or even collect samples to return to Earth. Each mission has contributed pieces to our understanding, gradually building a comprehensive picture of what the Moon is, how it formed, and how it has evolved over billions of years. The exploration of the Moon represents one of the great collaborative achievements of human civilization, with nations around the world contributing to our collective knowledge. The Soviet Union achieved a historic milestone when Luna 2 became the first human-made object to reach the Moon in 1959. Luna 2 was deliberately crashed into the lunar surface, impacting somewhere near the Mare Imbrium region. The spacecraft carried instruments during its brief flight that measured radiation and magnetic fields in cislunar space, providing the first direct measurements of the environment between Earth and the Moon. When it struck the surface, it also carried Soviet pennants, metal emblems bearing the hammer and sickle symbol of the Soviet Union, making them the first human artifacts to reach another celestial body. The mission was a propaganda triumph for the Soviet space program during the height of the Cold War, demonstrating technological capability and capturing the world's attention. It proved that reaching the Moon was possible and set the stage for the more ambitious missions that would follow, both robotic and eventually human. Just weeks after Luna 2's impact, Luna 3 achieved another first by imaging the far side of the Moon for the first time. In October of 1959, Luna 3 flew around the Moon and used an onboard camera system to photograph the hemisphere that had never been seen by human eyes. The spacecraft then developed the film using an automated processing system, scanned the images, and transmitted them back to Earth as radio signals. The image quality was poor by modern standards, grainy and low resolution, but they were revolutionary. For the first time, humanity could see what the far side looked like, and the images revealed its stark difference from the near side, heavily cratered and lacking the large maria that characterized the face we know. The success of Luna 3 demonstrated the technical sophistication of the Soviet program and whetted the appetite for more detailed exploration. It showed that with sufficient ingenuity, the secrets of the Moon could be uncovered even from 250,000 miles away. The Apollo missions represent the pinnacle of lunar exploration to date. Between 1969 and 1972, 6 Apollo missions successfully landed on the Moon, and 12 astronauts walked on its surface. These missions brought back a total of 842 pounds of lunar rocks, soil, and core samples, an invaluable scientific treasure trove. These samples have been studied by scientists around the world for more than 5 decades now, and they continue to yield new insights. The rocks told us the age of the Moon, revealed its volcanic history, showed us that it was once molten, and provided ground truth for understanding impact processes. Small amounts of these samples are still being carefully preserved for future study with instruments and techniques that don't yet exist. The Apollo samples fundamentally transformed lunar science and remain the foundation of our understanding of the Moon. They're also tangible connections to those missions, pieces of another world that you can hold in your hand, assuming you're one of the lucky few with access to them. Humans have only landed on one celestial body beyond Earth, and that body is the Moon. Despite decades of space exploration, despite sending robotic probes to every planet in the solar system and beyond, despite landing rovers on Mars and Venus, humans have walked on only one world other than our own. The Apollo missions remain humanity's farthest journey, the only time we've sent people beyond low Earth orbit, the only time we've stood on the surface of another world. This makes the Moon special in human history. It's not just our nearest neighbor in space, it's the only place beyond Earth where human footprints exist, where human voices have echoed across an alien landscape, where people have looked up and seen Earth hanging in a black sky. More than 50 years have passed since the last Apollo mission, and in that time, no human has traveled beyond low Earth orbit. The Moon remains, for now, the high water mark of human exploration, a reminder of what we achieved and a challenge to go farther. When the Apollo astronauts departed from the Moon to return to Earth, they didn't bring everything with them. Each mission left behind the descent stage of the lunar module, the lower portion of the lander that served as the launch platform for the ascent stage that carried the astronauts back to orbit. The Apollo 11 descent stage still remains on the surface in the Sea of Tranquility, exactly where Neil Armstrong and Buzz Aldrin left it in July of 1969. It sits there still, a monument to human achievement, slowly accumulating micrometeorite impacts and being weathered by solar radiation. The gold-colored foil that covered parts of the descent stage has likely degraded, and the metal itself will eventually be pitted by countless tiny impacts, but the basic structure will persist for millions of years. Along with the descent stage are scientific instruments, the flag the astronauts planted, their footprints, and various pieces of equipment. These artifacts constitute the first archaeological site on another world, and there are discussions about how they should be preserved and protected as heritage sites for future generations. China achieved a historic first in 2019 when Chang'e 4 became the first spacecraft to successfully land on the far side of the Moon. Landing on the far side presents unique challenges because there's no direct line of sight to Earth for communications. China solved this by first placing a relay satellite called Quqiao at a special orbital location beyond the Moon where it can see both the far side landing site and Earth simultaneously. With this communication relay in place, Chang'e 4 descended to the surface in the South Pole Aitken Basin, deployed a small rover named U-22, and began exploring this previously untouched region. The mission has provided unprecedented close-up data about the composition and structure of the far side, including potential evidence of material from the lunar mantle exposed by the ancient impact that created the basin. Chang'e 4 demonstrated China's growing capabilities in space exploration and opened a new chapter in lunar science by accessing regions that had been studied only from orbit. Among the unusual items that rest on the Moon is a small portion of the ashes of Eugene Shoemaker, a pioneering planetary geologist who helped train Apollo astronauts and made fundamental contributions to our understanding of impact craters. Shoemaker had hoped to go to the Moon himself as part of the Apollo program, but medical issues disqualified him. After his death in 1997, a small amount of his ashes were placed in a polycarbonate capsule and carried to the Moon by the Lunar Prospector spacecraft, which was deliberately crashed into a crater near the South Pole at the end of its mission in 1999. The capsule was engraved with images and text honoring Shoemaker's contributions. He remains the only person whose remains have been placed on another celestial body, a fitting memorial for someone who dedicated his life to understanding the Moon and other worlds. It's a poignant reminder that our exploration of space is ultimately a human endeavor, driven by individual dreams and curiosities. During the Apollo 14 mission, astronaut Alan Shepard, who had been the first American in space nearly a decade earlier, brought along a makeshift 6-iron golf club head that he attached to a sample collection tool. Near the end of the moonwalk, he dropped 2 golf balls onto the lunar surface and hit them. The first swing was awkward in the bulky spacesuit, and he only grazed the ball. But the second swing connected, and in the Moon's low gravity and airless environment, the ball sailed away, traveling, as Shepard enthusiastically reported, miles and miles and miles. In reality, analysis suggests it probably traveled about 200 yards, still an impressive distance. Those golf balls remain on the lunar surface, probably the strangest sports equipment in the solar system. The moment was light-hearted, a brief bit of play during a serious scientific mission, and it captured the spirit of adventure and the fundamentally human desire to bring a piece of home, even something as frivolous as golf, to new places we explore. Among the less glamorous items left on the Moon are 96 bags of human waste from the Apollo missions. The astronauts needed to minimize the weight they brought back to Earth to ensure their ascent stage had enough fuel to reach orbit, so they left behind everything that wasn't essential, including bags containing waste from the toilet systems in their spacesuits and the lunar module. These bags have been sitting on the lunar surface for over 50 years now, freeze-dried in the vacuum, preserved in a way that wouldn't be possible on Earth. Some scientists have suggested that future missions should collect and study these bags because they might contain microbes that survived the journey to the Moon and the decades of exposure to radiation and temperature extremes. If any bacteria or other microorganisms survived, studying them could teach us about the limits of life and help us understand whether life could survive transfer between planets on meteorites, a process called panspermia. It's an unglamorous aspect of lunar exploration, but it demonstrates that everything we leave behind has potential scientific value, and that the Moon preserves a record of our visits in ways both inspiring and mundane. Among the many firsts achieved during the Apollo 11 mission, one that's rarely mentioned in official histories but is nonetheless true is that Buzz Aldrin was the first person to urinate on the Moon. After the lunar module landed and before the astronauts opened the hatch to step outside, Aldrin needed to relieve himself. The spacesuits had built-in waste collection systems, essentially bags attached to tubes, and Aldrin used his while still inside the lunar module. So technically, the first human bodily waste deposited on the moon happened before anyone stepped onto the surface. It's a mundane, very human detail that reminds us that even during the most extraordinary achievements, basic biological needs continue. The astronauts dealt with many unglamorous aspects of living in their suits for hours at a time, and waste management was a constant challenge. These practical realities of space exploration often get glossed over in favor of more inspiring narratives, but they're part of the complete story of what it takes to explore another world. The moon has no weather in any sense that we would recognize. There are no clouds gathering, no rain falling, no wind blowing, no storms sweeping across the landscape. The absence of an atmosphere means there are no weather patterns whatsoever. Similarly, the moon experiences no erosion processes like those that constantly reshape Earth's surface. There's no water flowing to carve valleys or deposit sediments. There's no wind to wear down mountains or create sand dunes. There's no ice advancing and retreating to sculpt the landscape. The only processes that modify the lunar surface are impact cratering and the slow, gradual effects of temperature cycling causing rocks to crack and break down. This means that features on the moon can persist for billions of years essentially unchanged. A crater formed 3 billion years ago looks almost the same today as it did when it was created, slowly accumulating smaller craters within it but otherwise remaining frozen in time. This geological stability makes the moon a museum of solar system history, preserving a record that Earth has long since erased through its active geology and dynamic climate. Although the moon lacks weather and conventional erosion, it does experience constant bombardment from space debris. Every day, countless particles from micrometeorites the size of dust grains to larger rocks strike the surface. These impacts occur at velocities of tens of thousands of miles per hour, releasing tremendous energy despite the small size of many impactors. Over billions of years, this steady rain of debris has pulverized the surface rocks into the fine regolith that covers the moon. The bombardment continues today at roughly the same rate it has for billions of years, slowly but inexorably modifying the surface. Each impact excavates a tiny bit of material, mixes the regolith, and adds to the gradual process of space weathering that darkens the surface over time. This bombardment is one of the few active geological processes on the moon, a reminder that even without atmosphere or internal activity, the moon is not completely static. It exists in an environment that constantly shapes it, just on timescales far longer than we're used to on dynamic Earth. For all of human history until the space age, the moon's far side remained hidden from Earth, a mystery that could only be speculated about. The tidal locking that keeps the same face pointed toward us meant that no human had ever seen the other hemisphere. Ancient astronomers didn't even know this other side existed in a meaningful sense. They knew the moon was a sphere, so logically it must have another side, but they had no way to observe it, no way to know whether it looked similar to the near side or dramatically different. This changed in 1959 when Luna 3 sent back the first grainy images, and it changed definitively when astronauts orbited the moon and saw the far side with their own eyes. The Apollo 8 crew, the first humans to orbit another world, were the first to see the far side directly, and they described a heavily cratered, ancient landscape that looked profoundly different from the familiar near side. That moment when humans first saw the hidden face of the moon in person represents one of the great revelations in the history of exploration. The Moon has played a crucial role in stabilizing Earth's axial tilt over billions of years. Earth's axis is tilted at about 23.5 degrees, and this tilt is what gives us our seasons. But without the Moon, Earth's tilt would not be stable. Gravitational interactions with the Sun and other planets would cause Earth's axis to wobble chaotically over millions of years, swinging through a wide range of angles. This would create dramatic climate variations, with the poles sometimes pointing nearly toward the Sun and at other times being aligned more perpendicular to Earth's orbit. Such variations would make Earth's climate far less stable, potentially preventing the evolution of complex life. The Moon's gravitational influence acts like a gyroscopic stabilizer, keeping Earth's tilt within a narrow range that has remained relatively constant for hundreds of millions of years. This stability has allowed Earth's climate to remain relatively stable, creating the conditions necessary for life to evolve and flourish. We owe our existence, in a very real sense, not just to Earth but to the Earth-Moon system. The Moon's existence influences Earth's climate and tides in ways that have profoundly shaped the history of life on our planet. The tides raised by the Moon's gravity create intertidal zones, regions of coastline that are alternately submerged and exposed as water levels rise and fall. These zones are rich ecosystems today, but billions of years ago, they may have been crucial for life's transition from ocean to land. The rhythmic exposure to air and water in tidal pools could have provided the selective pressure that drove the evolution of organisms capable of surviving in both environments. The tides also dissipate energy through friction, slowly slowing Earth's rotation and lengthening our days, while simultaneously causing the Moon to recede. In Earth's distant past, days were much shorter and the Moon was much closer. The tides would have been far more dramatic, potentially playing an even larger role in Earth's early climate and the development of coastal environments. The Moon's gravitational influence reaches deep into Earth's story, affecting everything from the length of our day to the evolution of life itself. Throughout human history, the Moon has inspired myths, calendars, and science. Virtually every culture has stories about the Moon, explaining its phases, its motion through the sky, its influence on tides and fertility. The Moon appears in creation myths, in stories of gods and heroes, in poetry and art spanning thousands of years. Its predictable cycles made it a natural timekeeper, and many cultures developed lunar calendars to track the passage of time. The Islamic calendar is purely lunar, the traditional Chinese calendar is lunisolar, and even our primarily solar Gregorian calendar retains lunar influences in the way we calculate Easter. The Moon inspired early astronomers to develop sophisticated mathematical models to predict its motion, work that laid the foundation for celestial mechanics and eventually led to Newton's law of universal gravitation. The Moon has been a driver of human intellectual development, pushing us to observe carefully, to think mathematically, to reach beyond ourselves and try to understand the cosmos. Ancient cultures around the world tracked time using lunar cycles, recognizing the practical value of the Moon's regular phases. A month was originally defined as the time from one new moon to the next, approximately 29.5 days. This made the Moon's cycle a natural unit of time, longer than a day but shorter than a year. Agricultural societies used the Moon to time planting and harvesting, recognizing that certain lunar phases correlated with tides and with seasonal changes. Religious observances were often tied to lunar phases, with celebrations occurring at new moons or full moons. The detailed knowledge of lunar cycles developed by ancient astronomers in Babylon, China, Greece, and Mesoamerica was sophisticated and accurate, capable of predicting eclipses and tracking the Moon's complex motion through the sky. This knowledge was practical, used for navigation and timekeeping, but it was also part of larger cosmological systems that explained humanity's place in the universe. The moon connected people to the cosmos, providing a tangible, visible link between Earth and the heavens. Modern science continues uncovering lunar mysteries despite over 6 decades of intense study. Recent discoveries about water on the moon, about its internal structure, about ongoing seismic activity and shrinkage, all demonstrate that we still have much to learn. New missions are planned or underway from space agencies around the world, each designed to answer specific questions about the moon's composition, history, and resources. Advanced instruments are revealing details invisible to previous generations of spacecraft. Computer models are becoming sophisticated enough to simulate the moon's formation and evolution in unprecedented detail. Sample return missions are being designed to collect rocks from regions never visited by Apollo, potentially answering questions about the moon's volcanic history and the composition of its interior. The moon continues to surprise us, to challenge our assumptions, and to reward careful study with new insights. It remains an active frontier of scientific exploration, a place where fundamental questions about the solar system's history and the processes that shape rocky worlds can be answered. The moon remains humanity's gateway to deep space exploration. It's close enough to reach in just a few days, making it an ideal location to test technologies and develop capabilities that will be needed for missions to Mars and beyond. Future missions to the moon will demonstrate how to live and work on another world, how to extract and use local resources, how to protect astronauts from radiation and other hazards of the space environment. The moon can serve as a proving ground, a place to make mistakes and learn lessons before attempting the far more difficult and dangerous journey to Mars. It can also become a staging point, a place to refuel spacecraft with propellant made from lunar water, reducing the cost and increasing the capability of missions departing for the outer solar system. Many space agencies and private companies now view the moon not as a destination in itself, but as a stepping stone, the first step in humanity's permanent expansion beyond Earth. The moon that has watched over Earth for billions of years may soon become the foundation for humanity's future among the stars, a base camp from which we launch our journeys into the cosmos, carrying with us the light of consciousness to places it has never reached before, expanding the boundaries of what's possible and taking the first steps toward becoming a truly spacefaring civilization.